Oh no, you finally get to see what you've been missing out on. These are other causal inference tools. Some of you might be familiar with some of these, for example, outcome regression and propensity scores. Uh, However, I'm not going to be going over them, at least in the basic causal inference class. What I have gone over thus far is standardization. I want to give a very brief review of standardization. Standardization assumes that we are interested in the average causal effect in the population, that we can restrict our analysis to specific subgroups, as we talked about before. We simply strip the groups that we're not interested in from the population, and then we do our analysis on this subpopulation. So the average causal effect in standardization equals the average causal effect, that should be pretty simple, in each subpopulation, so L equals X, so for example, you are left-handed, times the probability that this subpopulation occurs. So the probability that this subpopulation is in the true population. So for example, for left-handed and right-handed people, 10% of people are left-handed, and so the probability of being left-handed is 10%. So if you remember from our original discussion, this was pretty easy. We would simply calculate the average causal effect in a small segment of the population, left-handed people, and then multiply times the probability of being left-handed. And this was nice when we had a few number of binary confounders. However, when we had lots of binary confounders, or when we had confounders that were continuous, we needed to rely on modeling. And so what we would do is we would assume the probability. So what we would do is we'd say, hey, every individual in our population counts for 1 over small sample size n of the possible weighting for the entire population. So we assume the probability by using our sample. And we estimate what the outcomes would be. So we had some sort of estimator for the outcomes, and we use this estimator to estimate the causal effects. So in standardization, at least the parametric G formula that we used last time, we assume the probability from the dataset, and we estimate the causal effects. Now, IP weighting, which comes from the same sort of family as standardization, they're both G methods, does the exact opposite. It assumes the average causal effect, and it models the probability. The only reason I showed you standardization was because I feel like standardization is a little bit more intuitive for me to explain and intuitive for me to grasp as well. This brings up one final point that I do want to make before going on to the other ones. There is another method here that I've not written up, and this method is simply a combination of standardization and IP weighting. So this is called doubly robust estimators. Doubly robust estimators. And simply, you combine standardization and IP weighting to get the best of both worlds. So remember, when we had standardization before, we had one problem, and that was we needed one new assumption in order to do the parametric G formula, in order to deal with these confounders that were continuous. This assumption was your model was not misspecified. This is a big assumption. With IP weighting, you need the exact same thing, except for the model is different. You're not looking at the model for the causal effect. You're instead looking at the model for the probability of the confounders in the population. So maybe you might get the standardization model correct, but you might not get the IP model incorrect, or vice versa. Doubly robust estimation will allow you to do both standardization and IP weighting, and its assumption is that only one of these models is correct. So you only need a correct model for the causal effect or a correct model for the probability of the confounders. So it makes that model misspecification claim or assumption a little bit less strict. Okay, finally onto a very brief description of the rest of them. So outcome regression and propensity scores, these are probably the most common tools that most people use in causal inference. That being said, there's a little bit more theory behind them, so you need to be a little bit more theoretically adept and mathy adept in order to get them. In addition, they don't as naturally transfer over to longitudinal data, so they get a little bit harder once we make that switch. So for those reasons, I've decided not to cover them in my causal inference course. The main reason basically is, hey, lots of people have done stuff on outcome regression and propensity scores. I can link some of their work down below. There's some stuff in YouTube, as well as some stuff, well, of course, as well as a ton of stuff in written format. The final thing that I did not mention, this is probably the most important, is G estimation. So this is sort of like the generalized form of standardization and IP weighting. The reason I didn't mention this is because, again, it requires a little bit more theory. G-estimation is really, really nice. The reason is because, well, the assumptions that you make in G-estimation are quite nice under panel data as well as under longitudinal data, and the techniques that you use are quite similar. That being said, because G-estimation is a little bit more theoretically advanced, it was much easier to explain standardization to you in this course. That being said, if you could only learn one more thing other than doubly robust estimation, G-estimation is a wonderful thing to learn. So that's about it that I'm going to be saying on these things now. Perhaps in an advanced causal inference course, I will get to more of these methods. That being said, there is so much material to cover that it's kind of hard to decide on what to do. So feel free to comment on sort of your opinion of these methods. Please leave as much vitriol out of it as possible, as well as on what you might be interested in seeing in an advanced causal inference course.